Hello everyone and welcome to the next session of Digital WE Days. My name is and I will moderate this webinar today, the session of Digital WE Days. Yeah, we are very pleased that you took the time to participate in our webinar. The topic today is Think Outside the Box, PoE Flyback with a Twist. Our speaker today is Mohamed Al-Alami, who is working as a field application engineer at Würth Elektronik ISOs. Before we start with the webinar, I would like to point out one thing. You will be mute during the webinar today. This means that you cannot ask us questions via your microphone, but you have the chance to ask your questions anytime via the Q&A tool. You can find us this below on the right side. Today's webinar will be about 30 minutes long. After that, we will answer your questions in a short Q&A session. If we are unable to answer all your questions within this time, we will answer them via email after the session. Last information for you, you will all receive the link to the presentation and the recording of the webinar, of the session of Digital WE Days in the next days. So now I wish you an exciting and interesting webinar. Thank you.
Good morning, everyone. I hope you've had a nice, relaxing weekend. I know I haven't. I've been working very hard in my back garden, but then we don't get very nice weather very often here in the UK. So when the sun is shining, you're out there usually. Anyway, enough of me. We start off with the presentation straight away, and looking through the agenda of today, we start by talking about just the general concepts and architecture for power over Ethernet. We look at things like signal flow and power flow. And then we will look at one key aspect, which is one of my experiences that I had with a variety of customers, is what options and solutions do we have from a PoE point of view. We will then proceed to look at a practical example of a power sourcing equipment design that I have done for one of our customers, just running through some of the challenges that we've had with that design, just to give you an idea of the twist, as I mentioned it in the title for this presentation. And time permitting, we might be able to go through example number 2. If not, the presentation slides will be available and they will be self-explanatory. So without any further ado, let's start off by looking at the concept and the architecture. And don't be scared. I know this is very basic and fairly standard, but I'm just trying to give an overview for everybody who might not necessarily be familiar with what power over Ethernet means. So it's basically passing the power, the electrical signal, along with the data lines on an Ethernet LAN system. 10100, 1G, 10G base T. You can use all of these different data rates to transfer power along the 100-meter cable, Cat5 cable, I should say. This is governed by a standard, which is the IEEE 802.3. And the idea behind this, of course, is as you are transferring data remotely to things like cameras or servers or phones sat on desks, you're also powering these devices at the same time, which means you're saving on extra adapters or plugs to get power to these components or parts. Okay, we're moving on. How did this standard progress over the years? So we started off with the 802.3.AF in 2003, and the power then was limited to 15.4 watt being delivered to the powering device. So that's the sort of 13 to 15 watts is what we were able to squeeze out or to send out to our device, be it the camera, the telephone, etc. And then in 2009, that progressed with the versioning of the standard to .AT, which allowed us a new type, which we call type 2. Sometimes people refer to these as PoE, PoE plus. The proper naming as per the standard is type 1 and type 2. And with type 2, we were now able to deliver around 25.5 watts worth of power to the power device. That allowed us to start moving things with motors, especially with CCTV cameras, to allow that extra ability through the higher level of power that is being delivered. Now, so far, the standard was only stipulating that you're able to transfer power over either the data pair or the spare pair, or either one of the two pairs if it's a 1G base T system. So on a 10100, either the data or the spare. On a 1G or a 10G, it's either one of the two pairs of data. In other words, you were limited in the amount of power that you can send across over those pairs. Now came the latest standard, which is the .bt, and that came up with two extra types, 3 and 4, and with types 3 and 4, now we are able to deliver much higher power, 50 watts, 70 watts, even up to 90 watts with type 4, if you know the channel length, or if it is, which is called the extended power capability. That's based on knowing the channel length. So that these two types 3 and type 4, you are able to transfer power now over all 4 pairs, and that allowed us that extra flexibility and the higher power capability, delivering capability. Okay, looking at the system architecture, just to show you how power flows, and again, this is probably quite basic. So just from a power sourcing equipment, this is where the power is generated, as you can see down at the bottom here. I'll use my laser pointer. So power is generated, and then it is introduced into the isolation transformer, which is taking the data in from the power sourcing equipment, and this is where the power gets mixed in, sent through an RJ45 connector over a Cat5/6 cable, and this is where the power now is delivered to the power device. At the connector, the power is siphoned off at the transformer end, the data goes through to the PHY, and then the power is regulated accordingly. So this is just an overview of the system. We'll go and dive a little deeper on the next slide to show you how actually this power gets moved through. So this is a more detailed system representation of the power flow from PSE on the left to power device on the right. What we're showing here is the isolation transformer, and this is based on a 10100 base T, so 2 data pairs and 2 spare pairs, basically, in the Cat5 cable. This is the RJ45 at the PSE end, this is the RJ45 at the PD end, and this is up to 100-meter cable between. So if we look through, the power is being transferred from the PSE through the center tap of the transformer onto the 2 pairs of Cat5 cable, picked up at the RJ45 at the PD end, and transferred through a bridge rectifier onto powering the PD side of things. And we'll talk about the PD controller and the isolated DC-DC in a little bit. And then the power comes back, or the current comes back, and it goes through the other data pair. Same route, pretty much, but of course in the reverse direction. And that takes us back and returns the power to the PSE. So the current flow in green and the positive returning back in on the negative polarity supply. Now, as I'm saying this, as I said to you before, types 1 and types 2, you could transfer the data over the data pair, you can transfer the power, I beg your pardon, over the data pair or over the spare pair. There is an option. It's called alternative A or alternative B. That's for types 1 and 2 only. You can't transfer over all 4. That's where types 3 and type 4 in the .bt standard came along. Let's move on. Let's look at a bit more of the nitty-gritty. You saw the PD controller and the PSE controller. So as part of this transfer of power, there has to be a certain type of handshake. And that handshake is what allows the power to be released. So how does that handshake take place? Let's look at a bit more detail into that system architecture. The first requirement of the system is the bridge rectifier. You saw that on the previous slide. And the reason for, or the need for the bridge rectifier is to ensure that if the polarity is reversed for whatever reason at the PSE end, then you are able to accept power in both directions. So basically the bridge rectifier ensures that the polarity at the PD end is the same all the time, be it the polarity coming in from the data pair or from the spare pair. So we need two bridges basically in this situation. The next thing is the signature. A signature is a type of a resistor, 25 kilo ohm specifically, a resistor that is placed inside the PD. The PSE, the power sourcing equipment, which is the one that's sending the power, will send a low probing voltage across to the PD to look for this 25 kilo ohm resistor. If it sees that 25 kilo ohm resistor, it identifies the PD as a valid PD to release power or to inject power to. So that's the first level of verification. As you see me talk about later on as well, there are now single event signatures and there's dual event signatures, single signature PDs and dual signature PDs, I should say. So we're talking primarily today about single signature PDs with a single resistor. So if it does not recognize this 25 kilo ohms, it will not inject power on the line. Let's say now it's past this level of verification. The next level is how much power. We saw type 1, type 2, type 3, type 4, and within these, we will talk in a little bit about something called classification. So within each one of these types, there are multiple classes, multiple levels of power that the PD requires. So these are defined by the classification. So the classification is another probing voltage that is sent across from the PSE to the PD, and through resistance on the PD side of things, it will detect a current flowing back and accordingly release the correct amount of power based on the class of that PD. All will become clear in a couple of slides when we show you some more of these classes and the levels of power accordingly. Now, I'm trying to make this simple. This is quite complicated in reality when it actually comes to performing this classification side of things. But we will talk maybe a little bit about that in a few slides in a bit more detail. Next is the FET, and the MOSFET that you can see here is, of course, the final stage of the release of power. So if everything goes well with the signature, with the classification, the next step is, all right, let us have it release the power to the PD basically. Once that voltage is released across, now you have to rectify that. You need a DC-DC, and that's what that DC-DC is there to do, is to take a variable voltage, 36 to 57. I've worked on designs where you can be down to 99 volts, beg your pardon, and up to 72 volts. It very much depends on what auxiliary supply sometimes that you also have that you have to run off. So in this DC-DC, you'll also need to maintain isolation. So it has to be an isolated topology, a flyback or a forward type converter. Predominantly, it's a flyback because it's a simple topology. But as power is increasing now, there is a case to go the forward converter way. So that sort of gives us a bit of a general overview of the internals. Now, let's look at how this actually works on an actual RJ45 with integrated magnetics inside. It's one of our product ranges that you see here. So this is the internal of the RJ45 connector, which has magnetics inside it. And what we are trying to show you here is it's also got PoE capability, of course. We're starting off with showing you the data path. So the data very simply goes through the two pairs, comes through the trifilar common mode choke, and note this is a trifilar, this is important, goes through the transformer onto the secondary side, and then ultimately onto the phi internal to the PD. So that's the data transferred through on one pair, the data transferred through on the second pair, transmit and receive. It can also happen over the other two pairs if it's a 1G or a 10G base T. Nothing to see here. Down at the bottom here, we have got the power side of things, but I'm not going to talk about that at this point in time. That's on the next slide. Here we go. And this is where on the same pair that we're carrying the data, we're now carrying the current, the power. So the current is split coming in from the PSE, like we saw on that earlier slide, is split between those two wires. So if I've got, just as an example, 1 amp, this would be carrying a 0.5 amp here and a 0.5 amp there. Those two 0.5 amps will be joined together on the center tap of the transformer and ultimately sent through the bridge rectifier to the power device. So that is the path in, coming back, path out through the bridge rectifier and onto that gray line, as you can see, and coming back and splitting through the two pairs, the other two data pairs, and back to the PSE. So that's the route for the power transfer, be it through the data pairs as it stands, or as you will see me show you in a second, on the data pair, on the spare pair, I should say. One very important point to keep here in the mind is this trifilar common mode choke. This is for your information, something that's quite useful. Is there is a balance here. You can see the two currents here would be equal naturally to the current coming through. So there is no saturation of this trifilar common mode choke as a result of the power currents. So it basically looks like a wire carrying the current. I need to keep that common mode choke there to do common mode choke rejection or common mode noise rejection for the data noise coming on the data pairs that we were showing on the previous slide. So that's something very important to keep in the back of the mind. Also, something that is important about the trifilar in particular, if you end up with an imbalance in the current on the two lines, albeit very slight. I mean, I know we're showing a massive difference here in the arrow size, but even if it is a small difference, this can cause saturation if you do not have this trifilar common mode choke. So that returning current naturally will ensure that the net flux in that common mode choke is 0. So again, it looks like a wire carrying the current. So there is no issues from a saturation point of view. Okay. Let's look at path number 2, which is through the spare pair. So exactly the same thing happens, but in this situation, those spare pairs are not carrying any data. This is a 10100 system, but like I mentioned as well before, this could be a 1G or a 10G base T, where these could be actual data pairs as well. No difference here whatsoever. Cool. Okay. So just to give you maybe a bit of a picture, just to also show you how this actually interconnects. So there is the power sourcing equipment with the RJ45 plugged in. Sorry, the Cat5 cable with the RJ45 in here. You plug in the cable in, and that's the route that we've shown before. And eventually that data goes into the PHY. And as an other option here, we also have a single common mode choke with both wires for the data pairs wrapped around the same core material. That's why you see this dotted line. So as opposed to, or as an alternative to that trifilar, what we have got is a bifilar, but to stop saturation from taking place, we wrapped those wires here and those wires there around the same core material, in which case both currents going in and currents coming out will give you a net flux in that core, which is one core, of 0. So there is no saturation as a result of power currents flowing through. So that's one option. Another option as well that you see in some of these RJ45 land transformers with magnetics built in is you also have the bridge rectifier built within the actual RJ45. It gets very busy in there, but that's also something that stops you from having to add an extra RJ45, a bridge rectifier external to the unit. So it's integrated or embedded within. That's an option. This is to show you how complex the internals of these components are. I'm showing you here a discrete transformer as opposed to an RJ45 with magnetics. So this is the internals of a 10100 1G base T. So you've got the two transformers and the two common mode chokes, the four transformers and the four common mode chokes for a 1G or a 10G base T. So as you can see, this is quite laborious and very much a complex build. So in addition to this type, which is very standard, and you've got quite a lot of these in the market, we also have introduced what we call a LAN automated quality. So in this situation, this is a pick and place type component where we have got the two signal transformers for 10100 and the two common mode chokes placed on a little PCB, which allows us the same functionality exactly as the standard discrete LAN transformers that you saw on the previous slide. But with this, naturally, everything is automated. The build of the transformer is automated, and the pick and place and the actual part itself is fully automated. We also have this available in 1G base T. Both of them are capable of PoE, up to 720 milliamps of memory. Now, so far, we've only been talking about type 1 and type 2. We've only been looking at a limitation of 25.5 watts, either spare pair or data pair. Now we've come to the .BT standard, where you can send power over all four pairs at the same time. So before it was either or, now you can send it over all four, and that allows us the higher levels of power, as I said, up to 90 watts with the extended power capability. Okay, so from an architecture, from a power device point of view, or even from a PSE point of view, there is a lot that we can support with. From a components point of view from Würth, this is just showing you a controller from ADI with quite a wide range of components that we can support on the input side of things, on the pre-control side of things. So from a LAN transformer and RJ45, common mode chokes, as well as the power side of things and the power conditioning with transformers and capacitors. So this is just to give you an overview of the level of support provided by us. Now comes the interesting part of the presentation in the types of solutions that we can offer. So I mentioned to you before, there is different classifications, and on this table it shows you with the .AF, which is the type 1 PD. We were limited to 13 watts at the PD pretty much, but there are now multiple classes within the AF to give us different levels of power required by the PD. And once the .AT was introduced to increase the power to 25 watts, now we have got a class associated with that, that's class 4. And the .BT, the last type, which is types 3 and 4 that were introduced in that standard, now we've got 5, 6, 7, and 8. So these different classes are important. If you remember back to what I was saying earlier, the classification is part of the handshake between PSE and PD to identify the power class of the PD. So now you understand the power class of the PD. How is this done? It is done by the ICs themselves, the handshake ICs. So this is a snippet out of one of the ADI X-Linear ICs, which gives you an indication of the type of classification resistors used and the nominal classification current based on the voltage that is introduced by the PSE to give you an indication of the different class of that PD. So this is very important, and this is called a class/mark event. So there is a number of these classification events that can take place, 1 up to 5. This depends on the PSE. So this is a whole set of seminars that I can easily go and talk about. I don't want to make this too complicated at this point in time. This is just to give you an indication of how we identify, based on the class, the power delivered or required by the PD. And now, how do we actually design a system from a PoE point of view? In my view, or based on my experience so far, and I don't necessarily come from a PoE design experience. I've designed in aerospace, power supplies, EMC, and so on, but not necessarily PoE. It's something that I've acquired as a knowledge throughout the years, basically working with Würth. And one of the solutions that we see on the market from a PoE system point of view is what I call the discrete solution. In this situation, you have two ICs, one dedicated for the handshake, like the one that we're showing here, and the second dedicated for regulating the power of the DC-DC flyback forward I mentioned earlier. This has got great advantages because it gives you total flexibility in the design. And one of the things that I've seen, at least during the COVID era, is that, of course, with the shortages of semiconductors, this was something that one of my customers wanted me to sort of do an assessment for him. And for me, it's a no-brainer. It's much better to use two separate ICs because of obsolescence. It makes it easier to find an alternative. If you're taking an integrated solution, as you will see next, the next couple of slides, then your redesign effort then doubles or becomes a lot more complicated and a lot bigger. So this is one of the solutions, and it gives you more options, like I was saying, with alternative ICs. The other solution is what I call the integrated solution, and this is where one IC does both the handshake as well as the regulation. Now, of course, this is less parts, it's a smaller PCB areas, then bound to be better layout and tracking. It's all internal to that IC. And you've still got the ability to add extra filtering for the power stage. So that's very important. So, and we'll see why on the next slide. But with this one, again, you are subject to having to do a major redesign if you are unable to get hold of this specific IC. Finally, the module solution. And the module solution is basically having everything in one box. You have the handshake, you have the DC-DC controller, and you have the actual flyback or forward converter in. Now, this is naturally the simplest solution. This is no layout and tracking. You just need to connect into your system basically for this. Much faster time to market. It's a no-brainer that this is a much quicker development and easier way to go about things. But there's two issues. One is, of course, what I mentioned before, is obsolescence and availability in the market. And the second, and for me more important, and this is something that we've seen with customers, is you have no access to the power converter. That's what this arrow is trying to show you. So from a PoE point of view of after the signature and classification, if you do not have access here, you are unable to add any extra filtering. Why? Because the IEEE 802.3 standard stipulates or says that you're not allowed to add capacitance at the input here that is more than 150 nanofarads, and an inductance no more than 100 microhenries. So it limits the amount of filtering that you can introduce here substantially. And that's based on the PD detection and rejection criteria sections, as I mentioned here in that standard. So that being the case from an EMI point of view, you are fairly limited in the amount of noise rejection that you can do. And we know flybacks in particular can be quite noisy, as you will see on the next few slides that I'm going to show you. So that covers the three different types of solutions. And I know I have not got a huge amount of time, but I'm just going to run through the first example fairly quickly. This is a PSE that I have designed for one of our customers. And I'll show you the twist. The twist is here in this transformer. So this transformer that you can see here is part of our product range. And that transformer, we had to flip primary to secondary as it was defined. So now the secondary is sitting on the primary side and the primary is sitting on the secondary side, basically, hence the twist, for it to apply to the spec requirements of my customer at the time. And that's something that you can really exercise when it comes to these types of DC-DC in particular solutions. So you can think outside the box. It doesn't have to be something that you have to customize from the word go. You can look at existing off-the-shelf components and maybe look at ways of manipulating them for your own spec requirements. This was a fairly high efficiency type component. or converter, I should say, we managed to achieve 80% wide range. We tested it actually up to more than an amp. So we did throughput about, I think 80 watts or 90 watts worth of power through this. And one of the things that we've also done, and we always like to do as Würth, because you know us for our EMI capability as well as power, hopefully, we've also simulated and tested this from an EMI point of view to just see the amount of noise that we are getting and the extra filtering that might be required for this. I've done this, by the way, by simulation of the parasitic components, interwinding capacitance, leakage inductance, capacitance of the drain source down to chassis, down to ground. As you can see, it's set right on top of a nice ground plane here to get rid of the heat. We've got our listen at the front end and our cable simulation or inductance simulation or estimation of the inductance of the cable. And we see with all of these, there's a lot of correspondence between the tested data and the simulated data. I'll go with the tested data here, and you can see here we've got a certain frequency of noise ringing on the drain source junction of the MOSFET. That's around 21 megahertz, as you can see here. And this is under a sort of a type 2 power throughput coming through from the converter. We then tested to look for differential mode noise, and that was done using an RTA 4004 oscilloscope from Roda and Schwartz. And you can do this with a split listen or a dual listen, or you can use this doing a math function, which is what I did in this situation. I just added the two RF outputs from the listen. And we also looked at the common mode output from that converter to see the amount of noise that we are getting. So we assessed both differential and common mode from the converter under full load conditions. And with no filtering, we got this type of noise signature. We introduced a PD, which is one of our series of differential inductors, 47 microhenries, and the noise dropped substantially, as you can see here. So that's without any filtering. That's with the PD in place, and you can see the differential noise reduced quite substantially in the lower frequency ranges. And then we finally introduced a common mode choke instead of, not as well as, instead of that differential PD inductor, and we've reduced the noise quite substantially. And I've got a question for the audience if you want to answer. You're going to ask me questions, I'm hoping, but before I finish, I'm going to ask you the question and I'm going to give you the answer. So why is a common mode choke so effective even in the differential mode range down here? So I'm expecting it to be effective here, where we saw there's still quite a lot of common mode noise. But I would expect it to be less effective down here. Why is that the case? Click on that Red Expert link when you get those slides, and you'll hopefully find out. So that covers my presentation for today, and I would like to say thank you. We can escape out of this and show. Okay. So this is just an overview, sorry, before I finish off, of our various different solutions that we have got available in terms of land transformers and power transformers. And with that, I close my session and I say thank you for your attention. I hope you found this useful, and I am all ears and ready to listen to your questions. Is there any software protocol? I can see there is a question here. Is there any software protocol involved with PoE? There are different software protocols, but from a hardware point of view, the hardware is what dictates. And if you're following the IEEE standard, it falls down to the hardware in the form of the signature resistors, the classification resistors, and so on. As part of the IEEE standard, it does allude to LLDP and various other different protocols that are used in PoE. And to be totally honest, I never refer to that side of things personally. I have always looked at this as a total hardware solution.
Okay, thank you, Mohamed, for the interesting presentation and for the answer for the question. So, yeah, I would say, yeah, we would like to turn our attention to your questions. When do you have any questions? So next questions. Why do you use a bridge rectifier in type 3 and 4 PD? This is not efficient.
Oh, yes, that's a very good question. Yes, the use of bridge rectifiers. Types 3 and 4 are higher current, and naturally, of course, with a bridge rectifier, especially if you're going towards the amp or even 0.6 of an amp, that will mean quite a bit of dissipation through the two diodes per pair as well, because you're going to have two of them running per pair, so it's going to be 4 diodes there. I do agree with you entirely, and I think for that, what we usually use is a set of MOSFETs, which can be controlled where you have got a much lower RDS on, and it's a lot more efficient a system. I would tend to agree with you on that point, but if you recall, the presentation was mainly on the 10100, where we were showing the bridge rectifiers, and that was mainly for a type 1 or a type 2. But as you go towards types 3 and 4, I would agree, yes, the better way to go about it is to use a control. And there are lots of ICs available in the market that can do this, that can do both. They include the FETs within, or you can add FETs externally where they can be controlled by an external controller as well. I hope that answers the question.
Okay, I think one last question. What is the best solution for PoE system?
Okay, so I mentioned 3 different types of solutions, and for me, I would suggest that it would be best to have 2 separate ICs as which is the first solution that I have mentioned on the slides. This would give you maximum flexibility, maybe a little bit more work, but I think it will make life a lot easier further down the line, especially in this time where semiconductors are in a better position, but not out of the woods yet. So allocation could be around the corner again. This will help with limiting the pain of having to redesign everything. So at least you've got 50% chance of a problem occurring. Hopefully it will never be the case, but you know, we from an engineering point of view, the number of people that I've spoken over the past couple of years that had to restart again is phenomenal. So yeah, that would be my suggestion.
Thank you. So now this is the end of the session. Thank you very much for your attention. Thank you, Mohamed, for your time and for the interesting presentation. So yeah, I hope you enjoyed our session of Digital WEE Days, and have a good day. Bye-bye.
Thank you, everybody. Have a nice morning. Bye.